So let's take a look at all the things we can say about these graphs. This is, for reference of this video, this is 523, A through D. We've already kind of looked at A and C. I'll go ahead and make this full screen so you guys can see what's going on up here a little better. I haven't done this in a while. Full screen, projector 2, there you go. Cool. So for A and B are pretty relatively straightforward because they're very much like what we just did in the previous lesson, just kind of backwards. This time I showed you the graph and I asked you to write the things instead of giving you the things and asking you to draw the graph. I mean, B and A have pretty much the same answer except you swap out a few things. I mean, the derivative at A is still equal to 0. There's a horizontal tangent going on there. So the derivative does equal 0, but the derivative now increases. F prime of A is greater than 0 for values of A that are less than x. Would be kind of the calculus-y way to say that statement there. In other words, it's increasing when A is, or x values that are, yeah. I think I got that right? No, I want to swap out x. I apologize. I'm getting my language all confused. F prime of x is greater than 0 for x that are less than A, because A is a fixed point. I don't want to move A. And then the other part is true. F prime of x is less than 0 for x values that are greater than A. So this is the calculus-y way of writing out that, okay, if you're to the right, then it's decreasing. If you're to the left, then it's increasing. And that change from increasing to decreasing is what causes the maximum to happen right there. When it comes to second derivatives, though, f double prime of x is less than 0, because it's concave down, for all x's. At least the x's that are nearby A. We don't know much about this function. We just know that pretty much it's concave down always. Now, the ones down in C and D, we'll just look at C for a minute. We wrote it down together a minute ago, but we'll just look at it for a second. This is interesting because the first derivative no longer is 0. That's not a horizontal tangent right there. That does not exist. However, would you still call that a minimum? Yes. I would too. It's the lowest point. If you're talking about just up and down, that is the lowest point. So there's a kind of a takeaway here is that it's not so much that f prime is 0 that causes the minimum to happen. Those can also happen when f prime doesn't exist. It's really this thing down here that matters, is that the graph changes from decreasing to increasing. That's what causes the minimum to happen. In other words, the first derivative changes sign, you might think about it. It goes from negative numbers to positive numbers. So it causes the minimum to happen. The second derivative also doesn't exist because the first derivative doesn't exist. But the second derivative is still concave down all the time. It's just a weird concave down on one side and a kind of a different concave down on the other side. The same set of things is true about D. We'll just write them together really quick. F prime of x does not exist, D and E, but f prime of x is greater than 0, increasing, for x values that are less than A, to the left of A. And the opposite is also true. F prime of x is less than 0, decreasing, for values of x that are greater than A. So this is still a maximum because of this thing right here. The graph changes from increasing to decreasing, which forces a maximum.
Is that Isaac?
What happened out there?
I have no idea.
Oh.
I hear it. Go ahead.
I just try to close the door sometimes.
Yeah.
Again, f double prime of A doesn't exist. Oh, I guess I should change this to A up here because
No, that should just I can tell when Isaac says option.
so again, the second derivative is positive. This is concave up for every value of x except for at A. So I would say for all x's that are not equal to A, like that. Pretty cool. As far as question E, really quick, and then we're going to do a doozy of a problem together and be done. Question E, if f has extrema at x equals A, then what do you know about f prime and what must happen to f prime at x equals A? So there's two takeaways I want you to have. If you haven't discovered them on your own right now, let's write them down. Two big takeaways from this problem. The first part of it, part A. If there is an extrema, meaning a minimum or a maximum, then one of two things must be true. Either f prime of A equals 0, or f prime of A doesn't exist. Yeah. This is how we can use calculus to find out things about functions without just graphing it and looking at it. There are other ways to get around this. But as far as the second part of this question, this part, the also part, that's probably more important, honestly. What must happen to f prime at x equals a? F prime of x has to change signs. Meaning it has to go from positive to negative or from negative to positive. And furthermore, that would tell you what's going on. If it goes from positive to negative, then you're going from increasing to decreasing, and that's a maximum. But if you're going from negative to positive, then you're going from decreasing to increasing, and that's going to cause a minimum, which I'm just going to abbreviate as max and min. Right now, this is kind of where you have to be with your understanding of this. It's not a very difficult concept, and we got to see it kind of two ways right now, which is cool. We got to see it forward and backward. We're about to apply this knowledge in great detail to a pretty hefty doozy of a just regular polynomial problem. So don't worry, I'm going to guide you through it. But get those calculators ready because things are about to get real. Speaking of which, I got to fire my calculator up so you actually see the live feed there. All right, let's go to this problem here. Let's talk about more funky functions.
Heck yeah.
Oh, yeah. Funky functions.
Funky desk.
Funky desk, funky functions. So we're going to use first and second derivatives to tell everything that we can about this function. We're going to do it mostly without a calculator. Actually, the last thing we're going to do is graph the original function and actually look at it. We're not going to need it, honestly, for most of this. First, let's start with A, which is really taking you back to your Algebra 2 pre-calc roots. We're going to factor the given function. And we're going to use our knowledge of polynomial functions to predict the number of local maxima and local minima that f has and justify your thinking. So let's go back to those pre-calc days, Algebra 2 days. That's okay. Don't worry about it too much. It's not super important for this lesson. But it does help to show that you can predict a good amount of stuff without doing any real work on this. As far as factoring things out goes, the only thing you really can factor out of this is the x to the 10th power that both of those terms have. So I would factor out x to the 10th, leaving with 10x squared for the first term and a minus 3 for the second term. Whack, as they say. Push and P, as the kids are saying.
No.
Am I using it right? Am I using that correctly?
What?
Push and P.
I don't know.
You aren't hit. No, this problem does not push P. I believe pushing P.
I don't know if it's appropriate or not. I was Googling it all 4th hour. I couldn't find an answer.
They're like the answers.
the best answer I got from the internet was if you have to look this up, you don't know what it means. And I'm like, yep, that's
It's not on Urban Dictionary.
all right, as far as roots goes, you got x equals 0, obviously. X equals 0 has what we call multiplicity 10. I don't know if you guys even remember. It's okay if you don't remember that. It's not important. That's okay. We used to do it in pre-calc, and it's one of those things we just kind of like, why are we doing this? It's not important.
That's where we didn't learn.
It just means that the 0, there are 12 zeros. There are 12 roots because it's x to the 12th power, and 10 of them are 0. That's it. The other two, if you were to solve this guy, set this equal to 0, 10x squared minus 3 equals 0, you would get x squared equals 3 over 10. And so it would be plus and minus the square root of 3/10. Not that it matters. This is not calculus. This is just algebra 2. So what it means is that this graph crosses the x-axis at those 3 locations. Actually, it doesn't cross the x-axis at 0. It just touches it. That's because it has an even multiplicity. We don't talk about this. It doesn't matter. Don't worry about it.
Wait, I do remember that.
Yeah.
That was in November.
If it has odd multiplicity, it goes through the x-axis, and if it has even, then it just touches it.
Not when we were virtual learning, so it's not.
There you go. Okay.
So we got
Okay. It doesn't matter. None of this matters. This is calculus. We're about to take the derivative of this thing. So, yeah. So I'm going to introduce you to a lot of important vocabulary along the way, too. Today is a very vocabulary-heavy day. A critical point is what we're going to call these from now on. So we've been dancing around this the whole time. Here it is in black and white. A critical point of f is any point where the derivative is 0 or where it doesn't exist. So that's it. Critical values happen when the derivative is 0 or the derivative does not exist. 9 times out of 10, when you're given a calc problem and you don't know what to do, you should take the derivative and set it equal to 0. Or see where it doesn't exist. That's what you're probably looking for. We call them critical points because we don't know if they're maximums or minimums yet. We just know that something interesting is happening there. It might be a maximum, it might be a minimum, it might be neither. But these points are called critical because they identify places where the graph might have a local maximum or a local minimum. So if you're given a question where you're asked to find the extreme value or the highest or lowest thing, this is a great place to start. This can narrow down your list of suspects very quickly. So we're going to do exactly that. We're going to find the maximums and minimums of this graph. We're going to write an equation for f prime of x, factor it, and then find all of the possible critical values. It's actually not too hard to do at all because this is a pretty simple polynomial when you get right down to it. F prime of x is going to be 120 x to the 11th power minus 30 x to the 9th power. Don't let that freak you out. It's not terrible. Just like we did with the original function, we're going to factor it, we're going to set it equal to 0, and we're going to find where those critical values are. So let's go for it. As far as factoring this thing goes, I would pull out 30 and x to the 9th. Those seem to be the common factors. Of course, if you multiplied by 4x squared, you would get the 120x to the 11th. And minus 1 for the second part, because that's just what it is, minus 1. And of course, we're going to set this equal to 0. Because we're looking for critical values. We're looking for places where the derivative either is 0 or does not exist. Since this is a regular old polynomial, the does not exist part, we can throw it away. But if we had like a square root or something, we would look for what makes that negative. If we had a fraction, we would look for at the bottom what makes the bottom 0. So keep in mind that you're looking for places where it's 0 or doesn't exist. So right now we're good. We're just going to find out where it's 0. A really easy answer, x equals 0. Because that's what makes this term equal to 0. That's a critical value. And it should be noted that it does have odd multiplicity, which will help you later on, but we'll get to that in just a moment. And then this guy over here, we actually do need to set this equal to 0 and solve it, but it's not too tough. If you do a little bit of algebra, x squared is equal to 1 over 4. If you add the 1 and divide the 4, and then you take the square root, all you got to remember is that whenever you take the square root, you have to put a plus or minus on the answer. So it's plus or minus 1/2. Because either 1/2 or negative 1/2, if you square either of those numbers, you get positive 1/4. So those are your 3 potential critical values in this problem. Let's make a list of them over to the side. Critical values. These are neither maximums nor minimums yet. We haven't determined that, but they are our list of potential subjects. Critical values. X equals 0. X equals negative 1/2, and x equals positive 1/2. Now comes the time where we learn about the first derivative test, which we actually have used a bunch of times in the past without calling it that. What we're going to do is we're going to determine and justify if those zeros or those critical values are local maximums, local minimums, or neither at each of the critical points. In other words, as we saw in the previous page, does f prime change from positive to negative at that point? Or does it change from negative to positive or neither? Those are the 3 potential options that can have. This is called the first derivative test, or FDT for short. Basically, you make a list of your critical values and you see, okay, does it change from negative to positive or positive to negative? A great way to do this is with a sign chart, which is exactly what we're going to make. We're going to put these zeros in order on a number line. Negative 1/2, 0, and then positive 1/2. And since this is a polynomial and it's continuous, we know that it's 0 at those 3 points. That means that in between those 3 points, it must either only be positive or negative. It can never change in those little ranges there. So a good way to do this is to just test one number and see what would happen. So like, for example, let's try negative 1, for example. Let's just test a point in that range. It's actually pretty easy to do because you have this, we have our factored form right here. What's nice about a factored form is it's just a multiplication problem. It's yellow times green. So if you know what the sign of the yellow part is and what the green part is, just think about, would that be positive or negative when you multiply it? You don't actually have to evaluate it. If you were to plug in negative 1, this whole thing would be negative because of the 9th power there. This would be 4 minus 1, positive 4 minus 1, so it's positive. You would have negative times positive, and therefore this is negative on this entire range right there. The same thing would be true, I think, if you plugged in positive 1. That's another easy one to do. This would be now positive 30, positive 3, be positive. So you'd have a positive range over here. The one that's tough, and I wouldn't blame you if you used a calculator to do it, and it wouldn't be too terrible, is these other little guys right there. Personally, I test negative 1/4. It's not too terrible to think about, or positive 1/4. You can choose any number you like in these ranges. Or if you know multiplicity, you know that this graph is going to go through the x-axis at negative 1/2 and then through it again at 0 because it's an odd exponent. So you could make a hypothesis and you'd be correct that it's positive and then negative like this. If you know your polynomials, it can help save you some time on this. However, if you test negative 1/4, this whole term becomes negative, and this right here, negative 1/4 squared becomes positive 1/16. But then 4/16 is less than 1. So that number minus 1 becomes negative also. It's negative times negative, and so it's positive. I don't have a better way to describe what I'm doing other than just telling you what's going on in my head. I don't feel like showing all the work in that. If you plug in positive 1/4 here, you get the same. This is positive, and this is negative, so you get a negative answer. But there you go. So all we're doing here is we're just testing one point on each one of these little ranges and seeing whether the derivative is positive or negative at that point. Now, since we've got this little sign chart, now it's really easy to look at the chart and go, okay, are these maximums or are they minimums? Negative 1/2 is where it goes from decreasing to increasing. That's a minimum. At 0, you go from increasing to decreasing. That's a maximum. And at 1/2, again, you go from decreasing to increasing. That's also a minimum. So at this stage, you have enough information to state that x equals 0 is a maximum, x equals negative 1/2, and x equals positive 1/2 are minimums. This does not tell you where those maximums and minimums are. It just tells you that they're located at this point. It doesn't tell you how high up and down they are. It just tells you that that's where they happen. That's an awful lot of stuff to digest, but we still have more, so we're going to keep pressing forward. Oh, here we go. Now, if you look at part C, you guys probably agree with this statement. The first derivative test can be time-consuming, which is true. Fortunately, there is another way, a debatably better way. Personally, I like the first derivative test for everything, but there is such a thing as the second derivative test, which is a lot faster. Fortunately, the second derivative also helps to determine the significance of many critical points. So let's think about f double prime. Let's go to the next level down for part C. We're going to do the same thing. We're going to write an equation for f double prime. We're going to evaluate f double prime at each point and answer the question, is it positive, negative, or 0? We're going to use our calculator for most of this, so don't panic too much. F double prime of x, going to the next level down. Keeping our first derivative in view there. What is 120 times 11? 1320? Yes. Be 1320 times x to the 8th power. Or sorry, x to the 10th power. And then 30 times 9 is 270 minus 270 x to the 8th power. That's your second derivative there. Oh, so much fun. We could factor this, but we don't really need to since we're not going to worry about the second derivative too much right now. So what we're going to do is we're going to use our second derivative to evaluate our three critical points. What's f double prime of negative 1/2? What's f double prime of 0? And what's f double prime of positive 1/2? Now this you probably are going to want to use a calculator for, so I'm going to make my calculator a little bigger so you guys can see it. Of course, I got to do some magic to make that happen. Man, that's slick. 1320 times negative 1 over 2 to the 10th power minus 270 times negative 1/2 to the 8th power. Stay with me, guys. So what we're doing here is we found the second derivative, and now we're just going to plug in the three critical values we identified from the first derivative. We're going to plug those in to the second derivative. So for the first one, 270. Whoops. Like, that's not the same answer that I got the first time. There we go. First one looks like I'm getting 0.234375. Doesn't matter what it is so much as that it's positive. it's a positive number. That's important for later. F double prime of 0 is stupid easy to get since they both have 0 as a x, so it's just 0. And the little calculator hack for you, if I arrow up to the answer, the thing I put in there, I can just delete the negatives now and get the positive 1/2. Which should be the same number since those are both even exponents anyway. Yeah. Which is also a positive number. I'll get my calculator out of there now because we don't need it. Now we're going to take a minute to ponder what this tells us. The second derivative tells us the concavity at a certain point. So what this says is that this is concave. I like Abby's method of saying CC. This is concave up because we got a positive number. The actual number doesn't really matter so much, only that it's positive. So we got 0.23 whatever, it's positive, so it's concave up. If f double prime of x is 0, this is what we like to say with the second derivative test. This is inconclusive. This doesn't really tell us anything. We already know that's a maximum from the first derivative test, and unfortunately the second derivative test does not give us any new information for this one. The second one, though, is also concave up. Now let's take a minute to look at question C, part 2. Recall that a function is concave up when its second derivative is positive, and it's concave down when the second derivative is negative. And we're asked to use this fact to verify our conclusion in part B. And this is called the second derivative test. Think about this for a moment here. We know that this the original function is concave up at this critical point, which means that it looks kind of like this. Sorry, concave up looks like this. And that is a minimum. The same thing is true with f double prime of positive 1/2. It's also concave up, and therefore a minimum. So the conclusion that I want you to draw from this problem is that you could test the first derivative to see the increasing and decreasing, or you could check the second derivative, because if the graph is concave up, you got a minimum at that critical value, and if it's concave down, then you got a maximum at that critical value. Now, this first derivative test and second derivative test are both two different ways to do the same thing, which is, I think, where students get them confused. They're kind of the same idea. Is your critical value maximum or is it a minimum? You can use either one to do this. So the only tricky part is when f double prime is 0. Usually that means there's a point of inflection, but this happens at the 1, 0 that's repeated like 10 times. It's no new information there. We already know that's a maximum, though, from the previous problem. Now, this is the stage of the game where we're actually going to take a look at the actual function, because we haven't done that yet. All this information came from us doing derivative stuff. So for question D, congratulations, we have found the locations of the local extrema. Now we're actually going to determine what those local extrema actually are. And we're going to use the calculator for that. We're going to look at the graph. So I'm once again going to bring my calculator to the front here. I'm going to make this full screen so you guys can see it better, because you're here live. And let's look at the original function. Let's go into our y equals menu and let's program that in. I forgot what the original function was. 10x to the 12th power. Holy God. Minus 3x to the 10th power. Oof. Why would you do these exponents so large? You could do this same example with much smaller exponents. I suppose it's all right. It's not terrible. As far as the window goes, we know these are all going to happen at like negative 1/2 and positive 1/2. So let's just go from like negative 2 to 2 on our window. And then I have no idea what the actual values are going to be. I'm going to try negative 10 to 10 and see what happens. I want to see something. Do something. There it goes. There's the first one. Oh man, you can barely make them out. Let's change that y a little bit. Looks like they're very shallow. That's negative 2 to 2 there. Oh, just barely. Wow. I mean, it does dip below. We know that's happening there, but I'm gonna go one more level down. I'm gonna go from like negative 0.25 to positive 0.25. Let's go. Let's zoom way in. I want to see it go below the x-axis. Come on. Oh, just barely.
Oh my God.
Wow. Yikes. Well, let's see what the calculator says. Let's go to calculate. Let's go to minimum. Let's go to the left of 1/2 and to the right of negative 1/2. And let's see what's going on right in the middle. Oh my gosh, it's so small.
That's what she said.
Stop. You guys are the absolute worst human beings in the world. Stop. Part of me wants to, my heart wants, oh, I'm so proud. I've never been prouder in my life. It's so good. Oh my god, I got a little brow sweat. That's good. Whatever. Okay. Wow, that's a tiny number. It's the same on the other side, though, I think, too. This is the problem, is now I'm thinking about that for everything. It's like I'm watching The Office all over again. It is. It's the same number. Okay. It's not worth writing down, but it's a very, very, very small number. This does have curvature to it. I wonder if I can get it to the side. Just going to keep going. I'm going to keep going with my regular math class as if nothing hit 7. Oh, there it goes. There it goes. Okay. Got it. I had to take it to -0.01 to +0.01 to see it. Then just got theirs. Okay, anyway, let's go to, let's talk about E and F. One last little thing to leave you with here. As if we haven't jumped a lot of stuff on you. First derivative test and second derivative test is a big idea. We're going to see it a lot. Maybe this will help. If you're going back to making corrections on your Chapter 4 test, this will probably help you with that one question that Kara Grosher basically had me do for her in advisory, and I didn't realize I was doing the question on the test. Whoops.
Nerd.
Oh, sorry.
I told you it was the test. You just
I didn't hear it.
You weren't listening to
I know. I never listen to anything anybody says.
You even heard me trying to tell you that this is
That's okay.
Should have listened, man.
That's all right. So here's one last little piece of this puzzle, is that question E and F. If you look at the graph of f of x, which we just saw, that very exaggerated graph, will f ever have a greater y value than its local maximum? So the local maximum happens at 0, 0, which if I look at the graph again, maybe I can bring it up on the screen right now. You can see the local maximum is happening right here at 0, 0. You can barely make it out because of the way this graph is so extreme. But the E is an easy question. Are there any points that are actually higher than that 0, 0? Yeah, there are a lot of them. They're all over here and all over here. So a local maximum is not the same thing as what's called a global maximum. This graph actually has no global maximum because it goes up forever on both sides. So that's the first conclusion for question E, is the difference between a global maximum and a local maximum. The local maximum is the 0, 0 that happens in this graph, but the global maximum in this case doesn't exist. So what, if anything, is the global maximum of f? There is none. There is no global max. When I was in high school, we called it an absolute maximum. If we draw a picture really quick of that same exaggerated graph that we just made, this will help a little bit to see it visually. You have kind of a graph, looks kind of like this. This right here is what's called a local maximum. Because if you zoom way in on it, it's the biggest thing going around in its neighborhood. However, on both sides, there are x values that go way up to infinity, in fact. So there's no global maximum. If I were to put a thing on this graph that maybe turned around and went back down this way, this would become the global maximum. Well, anyway. These other guys down here, though, in the next question, likewise, will f ever reach a lesser y value than its local minimums? Actually, it should be minima because they're actually the exact same number. If not, then the global minimum is the same as the local minimum. And in this case, that's the case. The local minima, since they both happen at the same very, very small number, the local minima are at x equals -1/2 and x equals +1/2. Or, global minima. In short, the whole point of this problem is that the global minimum is the absolute lowest point you see on the graph. And sometimes, if it goes down to infinity, there is no global minimum. The same thing would be true of maximum. There's a better picture of this on the next page of your packet, which has this math notes box in here. And this does a really good job of explaining it, that diagram right there. So this picture does a good job of explaining what's going on here. You have two local maximums, one at this orange point, one at this red point. Those are, in both cases, that's the highest point in their little neighborhood. but there is actually no global maximum because this graph goes up forever like this. So there's no global maximum. You have a couple of local minimums. You have one right here at this green point and one right here at this blue point. But this end point over here is the lowest point in the land. And since it's an end point, it actually is the lowest point. So we would call that the global minimum. It's the absolute lowest point on the whole graph, like that. Now there's one last question to talk about, but we're going to run out of time pretty quick. But you will see it on the homework tonight, which is good. And I don't like question G anyway. I like the question that pops up later on much better. You'll see it in 527. If you look at the YouTube video that I recorded on Friday for this, the YouTube video is like 35 minutes long, and a good 15, 20-minute chunk of that is me rehashing the same things we just talked about on this problem in particular. So look at that, I would say, for more help on this one. And what's going to happen in C and D specifically is, let's say if you put some endpoints on this thing. What if you start putting some different goalposts on this? In those little ranges, there is going to be an extreme value. So maybe one last thing to leave you with is the thing called the extreme value theorem, which is at the very bottom of this math notes box. And the extreme value theorem says that if you have a closed interval from A to B, like you put some endpoints on this thing, there will be an extreme value. There will be an absolute maximum and an absolute minimum. It's either going to be at one of the critical values or at the endpoints. But you'll see us talk about that, and we'll mention this again in another video. So hopefully this is helpful to you, Vivian, if you watched it. And hopefully you heard that amazing joke, and I have it now on video forever. So I can't wait to watch it.